In this video, we will continue with the basics of IV. In video 1 of this lecture, we finished by we talked first about the general idea of instrumental variables and started formalizing instrumental variables in this way, whereby we have a first stage based on which we predict the treatment. So the treatment is predicted based on the instrument, and then we plug this treatment into the relationship of interest, and that gives us then a consistent estimate. If the instrument is valid, it gives us a consistent estimate of the relationship of interest. We want to take another look at the mechanics of instrumental variables, which we will encounter over and over again in this course. And if you do empirical work, you will encounter them over and over again. So one important thing to notice here is that the IV estimator, beta IV, so the estimate that you would get when you run an IV regression in any statistical software, is nothing more than the reduced form divided by the first stage. And we will see later what the interpretation of that is and why this is so useful. Okay, so the reduced form, remember, is this regression here, and we also know from undergrad econometrics what the estimate for gamma 1 is, which is nothing more than the covariance between the outcome and the instrument, in this case conditional on X, over the variance of the instrument conditional on X. Right? That's what the reduced form is. For the first stage, the same. The estimate for delta 1 is nothing more than the covariance between the treatment and the instrument, in that case also conditional on X, divided by the variance of the instrument conditional on X. So what does that, so these are just two regression coefficients, and what this slide here tells us is that the IV coefficient, so the coefficient that we get from the second stage, is nothing more than the reduced form divided by the first stage. So what I do here is I leave out the conditional on X for simplicity. It's not important here, but I want to quickly derive that. So let's start with the covariance, or let's start first of all with the relationship of interest. So the relationship of interest is y equals alpha plus beta d plus u. That's the relationship of interest. So we're interested in the effect of the treatment on the outcome. Then what we want to look at is this covariance that forms part of the reduced form, which is simply the covariance between the outcome and the instrument. Now what we can do is we can substitute in this equation here, we can substitute this in here, which we do as follows, is alpha plus beta d plus u. And then what we do is we will simplify things. This has to be obviously the covariance of this sum with z, and the covariance of a sum with a random variable is the sum of the covariances of each of the terms with the random variable. Right? So the covariance between a scalar, which is alpha, the intercept, and the instrument Z is 0, so that we can just discard. So we have the covariance of beta D with the instrument plus the covariance of U and the instrument. Now, beta here is a scalar. It's the population parameter. It's the relationship in the population that we want to study, and there is only one, so it's deterministic. So beta is a constant, so we can pull it in front of the covariance. So that's beta times the covariance of the instrument and the treatment. And if the instrument is valid, then that covariance is 0. So that is obviously only the case if it's a valid IV. If it's a valid IV. If it's not valid, then obviously we have a bias. And now we simply need to solve for beta. So beta equals the covariance of the outcome and the instrument divided by the covariance of the treatment and the instrument. And so this is exactly what you can see up here. And we will see later and also in future lectures why this is such an important insight. Now, to illustrate this, I'm choosing a classic example of an IV study, which was a large randomized control trials in the 90s in the US called Moving to Opportunity. So the idea was that you had in several US cities, you had very poor neighborhoods, and the concern was that with lots of public housing there, and it's very hard for people to move out of these neighborhoods. And the question is, would moving out of that neighborhood actually improve the opportunities of the people who move, right? So the parents and also then the children. And so there was a large-scale field experiment done in several US cities in 1996, where there was 3 groups. So you had 2 treatment groups and 1 control group. The treatment groups, so one treatment group got a voucher for private rental housing in a low poverty neighborhood. So they just received in the post a voucher that said you can move to a low poverty neighborhood. We will cover your moving costs. We will cover whatever the school fees for your children. So they made it really attractive for those people to use that voucher to move. The second treatment group received also a voucher, but it was less restrictive. So the first group had to move to a low poverty neighborhood. The second treatment group just had to move, or if they used the voucher, they could move anywhere into private rental housing, whereas before they were living in public housing. The third group is a control group. They didn't get a voucher. So it's not that they were forced to stay put, but at least they didn't get any financial incentive or any help in moving. And so here you can already see what an instrument typically is. It's an economic incentive or an invitation or an offer to get treated. It's not it's not an experiment, or it's not an experiment in the sense that everyone is forced to take the treatment, like you would have maybe in some medical trials or in experiments with rats or so. Whereas here, we deal with people make choices, and thankfully no experimenter can and should force people to do anything. So all we can do is we can give some people a greater incentive to do something than others, and then see what happens, to the extent that this is ethical and so on. That's what happens here. So the instrument is basically those vouchers, and those vouchers provide people different economic incentives to move away from their neighborhood. And so what the experiment shows is the following. So first of all, when we look at the number of people who actually moved, it was about 50% of those who received a voucher. So the take-up of that voucher was actually huge. And most of them also moved to better neighborhoods. So you can see this here when you look, for example, at the average poverty rate in a neighborhood. So in that case, in a census tract, and you can see that among those people in treatment group 1, that's these guys, that's treatment group 2, they moved to a neighborhood with a lot lower poverty compared to the control group. And the same goes actually for the treatment group that received a voucher with no strings attached. And the same thing goes then for street safety and crime and so on. So it really, that this was the first stage. Basically, it shows that the vouchers actually induced people to move to better neighborhoods. And now we want to see, well, did this actually then have an effect on the outcomes? And here, let me pause here for a second and let's think about what would be the relevant policy questions here. And I can think of at least two. One is to say, what is the average effect if I take a random person from a poor neighborhood and move them to a rich neighborhood? That's one policy question. But I might not be able to do this as a government for ethical reasons, but it might still be an important question. It's like, how much better would those people be off if they just moved to a better neighborhood? That's one question. The other policy question is, as a government or a local council, how effective are those vouchers? And that is basically that is the reduced form, because it tells me then if I give a person a voucher, to what extent does that not only induce them to move, but to what extent does that improve their outcomes ultimately? These are two different questions. Both are policy relevant. Which one is more important depends on the policymakers, what they want to know. But what instrumental variables do, or what the IV framework does, is it relates those two questions and allows us, under assumptions, to give an answer to both. Not a perfect answer, but it allows us to give an answer. So, this slide pretty much summarizes what I already said about the different effects one can look at. So you have here the instrument, you have the treatment, but obviously not everyone who received a voucher actually moved. And so then it depends, do I want to know what is the effect of moving on outcomes, or what is the effect of receiving a voucher on outcomes? And the reduced form, the effect of receiving a voucher on health and education outcomes, that is also oftentimes called the intention to treat effect. So you will encounter this expression a lot if you read papers, which is that this variable Z is one, not if a person moved necessarily, but it's one if the person got a voucher. Okay, so basically the people who got the voucher, they were invited, they were incentivized to be treated. And that's what, loosely speaking, intention to treat stands for. Okay, and intention to treat can be important for policy evaluation. Again, here the example is, as a local council, I can't force people to move, but I can provide those incentives, and I want to know perhaps how effective are those incentives, right? So then I would want to run that regression down here of whatever outcome I'm interested in. I don't know, education outcomes of the children, health of the children, something like that, on whether a family received a voucher or not. And if I find a large estimate for gamma 1, then that would indicate that those vouchers may actually be quite effective. How cost effective is a different question, but at least in terms of achieving what they should achieve. But suppose we are interested in the other question, which is what is the causal effect of moving? And that's what we can actually get from the IV estimator under those conditions that we have learned before. So we have Z, the instrument is as good as randomly assigned, and it has no direct effect on the outcome. So that second one is called the exclusion restriction, and this is sometimes called conditional independence. And then the third one is the first stage, which is that obviously the vouchers should have a sufficiently strong effect on the likelihood of people actually moving. Okay? And so if these three conditions are fulfilled, then we can actually also estimate what is the causal effect of moving and not just the causal effect of receiving a voucher. Okay, so how do we do that? Or and are those conditions fulfilled here? Well, the third one is the easiest. We've seen this on one of the previous slides. So people who received a voucher were more likely to move and were more likely to move to a lower poverty neighborhood. The instrument is as good as randomly assigned. That's just part of the experimental design. They made sure that it was purely random, that it's not that poorer people were more likely to get that voucher. And it's also, this is what we have to assume, it had no direct effect on the outcome. So it's not that people received those vouchers and that changed their choices. That's an assumption one has to make. That's debatable, but let's for the moment assume it's true, which I believe in this case is true. Now we can relate. So from this, with this information, we can estimate three causal effects. Okay? The first is the causal effect of receiving a voucher on moving. Okay? Which we simply do by the following. So for each. So within the sample, we can estimate this by comparing the probability of moving, so this is D equals 1, of those people who received the voucher versus those who didn't. Right? So there was also obviously people who did not receive a voucher but yet moved. The question is just, was the number, or in that case, the share of people who moved, was that higher among those receiving a voucher? And that's what we've seen. Then we can look at the reduced form, which is the intention to treat effect, which is what is the average outcome of people who received a voucher versus those who did not. Okay? But what we're actually interested in is the treatment effect of interest is not who received the voucher and who doesn't, but what is the average outcome of those people who moved versus those who didn't. And how we bring all those three together is through the so-called walled estimator, which is what you see here at the bottom. And so you see here that the treatment effect of interest is the intention to treat effect, and in IV speak we often say scaled up by the first stage. And I will provide an interpretation of that in a second. So here's the example. So suppose that the difference in outcomes between people who received a voucher and who didn't is 10. Okay, so let that be 10. And we know that 50% of the people who received a voucher actually moved. And let's assume for simplicity that no one else moved. So that the first stage here is a difference in 0.5. Okay? And so then we can calculate from that the actual IV estimate, which is 20, right? 10 over 0.05. Now, how should we think about this? We obviously went about it in a very roundabout way. Let's think about it the other way around. Suppose for everyone who did move, the effect is 20. So their outcome, I don't know, their health status improved by 20 points, whatever 20 points means here. Now, how can we split this up? Well, of those people who received a voucher, 50% moved. Right? And for each person who moved, their outcome increased by 20. Right? And then 50% times 20 is 10. That would give you then the intention to treat. And that's how you can interpret the intention to treat. Again, that's just the causal effect of receiving a voucher. And obviously, if you want to get the causal effect of the treatment, you have to factor in that only a fraction of those receiving the voucher actually then took the treatment. And then you arrive at the actual causal effect. Now, one caveat here about this causal effect that will also come up over and over again when you work on using IVs is that it's a causal effect, but one has to ask the question, well, it's a causal effect representative of what population? Does it represent the average effect of just taking a random person from a poor neighborhood and putting them into a rich neighborhood? No, most likely not. Why? Because here what has been randomized is the incentive, but obviously people may differ in their likelihood of responding to that incentive. So for some people, it's way more beneficial to move than for others. And so we only then observe that the difference in outcomes, or the favorable outcomes for those people who eventually moved. And these may be a selected sample or a selected subgroup. So even though it's a causal effect, it may not be representative of the population we actually want to study, because it's so much more beneficial for some people to take the treatment than to others. Later in this lecture, we will talk about marginal treatment effects, which allows us to get a better handle on this idea that some people are more likely to take the treatment rather than others, and which gives us tools that allow us to extrapolate from this selected subgroup that chooses to take the treatment to broader groups, or even to the whole population. Now, what they do here in that paper by Kling et al. Is for different outcomes, they actually, which is very nice, they report those different parts of the Wald estimator. Okay, so the Wald estimator is the treatment effect on the treated, and that's the intention to treat effect divided by the first stage. All right, so you can see here, if you divide 0.048 by 0.4678 or something similar, you arrive at minus 0.1. Right? And so what the experiment has shown is that it's the experiment was hugely beneficial for people. So you could see that alcohol use, drug use went down, anxiety went down, mental and physical health, and so on. So this showed that it was a successful experiment. Okay? But I'm not showing you this because I'm such a big fan of this experiment, but simply because it illustrates very much the building blocks of IV estimation. Now here's another study that is a classic instrumental variables paper by Josh Angrist and Bill Evans, which came out in 1998 and has since been replicated in many contexts. So the basic question here is whether having children and whether the number of children affects female labor supply. Okay? This is obviously an important policy question when it comes to gender equality, when it comes to inter-household allocation of resources. We want to know whether, as women have more kids, whether they reduce their work hours, and whether they do so in a subsequent analysis, maybe more so than men. And then we can think whether that's desirable or not. The problem is, if we run such a regression as is shown here, of the number of work hours on the number of kids, the number of kids is most certainly endogenous. Okay, so fertility is a choice. Yeah, there can be a random element to it, but many people plan their fertility and so on. And at the same time, labor supply is a choice. And you can be certain that if you regress the result of a choice on the result of another choice, that there will be some common elements to those two choices that introduce a spurious relationship. Right? So, for example, if a family is richer to begin with, think they made a big inheritance, or they just have a huge, have one person who has a huge earnings potential, they can afford to have more children, and also are more likely to afford that one person stays home with the children. Okay, and then when we look at different couples, there may be some, couples differ very much in their preferences over fertility and labor supply, depending on cultural background, age, and so on. Okay, so almost certainly the conditional independence assumption, which is this one here, is violated. And so we have to obviously then find a way of dealing with that. And Angrist and Evans, what they do is they use an instrumental variable. But before we do that, and before we run any or start any causal study, we should always think about, well, what is the ideal experiment one would run if you could? Obviously, you can't just randomly assign children to families, but that would be the ideal experiment, right? So if I wanted to do away with this correlation here, which is that families who would for other reasons have higher or lower work hours also have more or less kids, and that's a systematic relationship. One way to break this would be if I could randomly assign the number of children to families, right? And so then I could see how I could attribute the changes in labor supply or the differences in labor supply across women to the number of children. Otherwise, it could be anything, family backgrounds and so on. So what Angrist and Evans do here is they use as an instrument the sex of the first two children. So they consider a sample of women, of women who had at least two children. Now, how does this instrument work in theory? And this is actually a good example for walking you through how you would go about such an analysis. It's not that you start with the empirics first and foremost, you would first start with what is the ideal experiment? It's not available, but what is the benchmark experiment that I would run if I could? Then I think about the identification, which is, in a perfect world, theoretically, how should this work? How would I break this correlation here theoretically? And then I go on to estimating it. So what they do here is they exploit here that couples in many countries tend to have preferences for mixed sex offspring. Okay, so people prefer having a boy and a girl, as if they have 2 kids, to having 2 boys or two girls. Why is that the case? I don't know, but this is consistent with survey evidence, is consistent with anecdotal evidence that, you know, when I ask around my friends, that I can gather. And so what they exploit here is that couples who have 2 boys or 2 girls as their first children are more likely to have a 3rd child. And so so the idea here is that the gender of the first 2 children is randomly assigned, and so it's then random if a person has or if a couple have 2 children of the same sex or of opposite sex, and then we and if they do have children of the same sex, that may increase their likelihood of having a 3rd one. And that gives them basically this first stage, this margin, where some couples who are treated with same-sex children would have another one, which then gives you an increase in the number of children that couple has. Now, some people, when I introduce this, I also show this to the undergrads and say, yeah, but maybe couples won't. Yeah, as we see, not so many couples do, but some do. And then the question is it a strong enough first stage? So is the response strong enough to draw meaningful conclusions? And this is perhaps more important here, are those people who then, once they are treated, choose to have a 3rd one, are they representative of the broader population? And most likely not. Okay? And so then we need to think how to interpret the result we're getting. So what we're doing here is the standard protocol. So the first stage is the number of kids regressed on a dummy for whether the first 2 children were of the same sex or not. And then the reduced form is the number of work hours regressed on whether the first 2 children were of the same sex or not. The exclusion restriction here is that whether the first 2 children had the same sex or not is unrelated with personal characteristics. Now, this may hold obviously in quite a lot of countries. There are some countries where you have selective abortions where that may not hold, but in many countries it probably does. One of the few things that is truly randomized. Okay? And so when we look at the data, you can actually see this. Okay, so roughly 50% of all families with 2 or more children, the sex of their first 2 children should be the same. So that's what we would expect, and if that didn't come out, that would obviously be a red flag for our data set. So then let's look at a benchmark OLS regression. So here we regress the number of work hours on the number of kids, and we see that every additional child above 2 decreases weekly work hours on average by 2.66. So the average woman works 28.5 hours, but with every additional, the average woman with no kids works 28.6 hours, but with every additional kid, the number of hours decreases on average by roughly 2.7. But we know that that's biased because people who have more kids may have chosen to have fewer, a lower labor supply, even in absence of having fewer kids, having more kids. So that's why we use the IV. So let's first look at the first stage, and you can see here that the instrument has a first stage, but it's not very, very strong, right? So so economically, it's not very strong. So what it tells us is if you have if your first two children have the same sex, those couples have 0.7 more kids than on average per couple than couples who have mixed sex children. What does this mean? It means that basically I didn't exactly work it out, but it's something like of 13 couples who have two children and their two children have the same sex, one of them decides to have an additional child. Right? But it's statistically significant, and it's, at least in their paper back in 1998, was considered a strong enough first stage to draw a meaningful conclusion. There is, we will come to that in later videos. There is now a discussion of when are instruments strong enough to draw such a conclusion, but at least we see here that there is a response. It's not huge. Most kids who have either two boys or two girls don't bother with the third one, but some people have more. So the number of kids, of additional kids among those people whose first two kids were of the same sex was significantly higher than among parents who did not have, whose first two kids were of opposite genders. Okay, so now the IV estimate is the following. When we put this all together, so we have the reduced form and we have the first stage, we can also just do this in one go, and we see that now the effect is a lot stronger. Okay. So we see that an additional child reduces work hours on average by 5.5 rather than 2.7. So the effect almost doubles. Now, what's behind this? Again, here, let's just think about the interpretation of the IV using the intention to treat, or the reduced form. So you can see here the reduced form. And here you see that the effect of having children of the same sex on work hours is negative and statistically significant. It tells us that women whose first children were of the same sex work per week on average about 0.4 hours less, so about 20 something minutes less. Okay? This is a small effect, but it's statistically significant. Now, it's a small effect, but mind you, this is also the reduced form. And previously we've seen that it's only very few women who actually respond, or very few couples who respond by having another child. Okay? So what this gives us is basically the reduced form tells us that, yeah, among the population where one couple in 14 responds to the treatment, the average difference is 0.4. What we are asking with the IV estimator, by scaling it up with the first stages, well, what would be the difference if every couple responded that has two children of the same sex, if every couple had a third child? That's what the IV estimate tells us here, which is equivalent to what would be the response of the average couple having a third child. Okay, so once again, the instrumental variable estimator is the reduced form minus 0.39 divided by the first stage, which is 0.07, and that's when we arrive at minus 5.5 something. So once again, the having same-sex children increases or decreases the number of work hours by 0.4 on average, but remember that only a very small fraction had actually responded to the treatment. Now, if we scale the reduced form up by the treatment, which means that not only 1 in 14 couples decides to have a third child after having 2 children of the same sex, but suppose every couple who had children of the same sex, 2 children of the same sex, decided to have a third one, what would be the effect then? And that's the effect that we've estimated here. An additional question here is, now we have obviously only been able to identify this effect over those people who responded to the treatment. Those who did not respond, so those who had 2 boys or 2 girls and chose not to have a third child, they are not relevant for this estimation here. And we will see this when we talk about local average treatment effects in a future video. And so to what extent those people who actually respond to the treatment are a relevant and interesting group to study, that's up for debate. And that depends on the context and on the question one would like to answer with it. But be aware that it's not typically the population one is actually interested in. That's a trade-off. So you can either provide a causal effect for a subpopulation, or you can provide a biased effect, a biased estimate for a population you're interested in. The challenge is bringing those two, optimizing between those two. So to wrap up videos 1 and 2 for instrumental variables, we've introduced here instrumental variables as an important tool of causal inference. So what instrumental variables do is they leverage variation in the treatment that is driven by the instrument and unrelated to confounders. But there are 2 challenges with it. Finding a valid IV is difficult because the exclusion restriction is untestable. And the second challenge is that it's not random who responds to the instrument. And so IV estimates are causal, but they're not necessarily representative of the population we are interested in. And that's something to keep in mind, and that's something that obviously economists have a lot to say about where we can actually use constrained optimization from microeconomics to provide some insights into this process of who is likely to take up the treatment and who isn't.